Ioannidis, he's probably the most famous scholar doing this kind of work right now. He's, on TV, he writes op-eds, he's basically has been writing about these issues for a long time, and he's having a lot of impact in medical research and now beyond. So this is the most famous of his pieces, and he isn't shy. He boldly states the problem. Most research findings are false for most research designs and for most fields. So he's basically saying the median paper you read is probably a false positive. That's his sort of take on the world, and he actually has put together a lot of evidence suggesting we should take that claim seriously. I don't know if that's true or not, that claim, but even if there's only some chance it's true, it's very worrying. So we have to sort of take it seriously. And what he does in this piece is he doesn't really provide evidence for it in this piece. This piece is really a thought experiment. This piece just lays out some of the basic probability theory or sort of statistical theory and sort of walks us through why we should be concerned about this problem. Let's just go through some of these terms. So R is the ratio of true findings to not true findings in an area. So what does that mean? Well, first of all, caveat here, he really sees the world, and it's simple to see the world in this way, as a 0-1 world. There's a test, it could be true, it could be false. Maybe this is like coming from the medical world, like a drug, helps a patient or that doesn't help a patient. Maybe that, that's why he's thinking of it that way. Of course, in reality, the world is very continuous. If we're thinking of famous empirical literatures in economics, like the literature on the returns to education. But, let's just stay in Ioannidis' world and just think of this simple binary world. This has an effect. It doesn't have an effect. It's simple to think of it that way. But what does this ratio mean? This ratio is, imagine there's a certain realm of activity. So development economics, let's say we're interested in interventions to improve education in developing countries. How many of those interventions will have a positive impact on learning? For how many of them will there be an effect? Okay, so that's sort of what R is going to capture. Maybe if you tested 20 of these, maybe it's 10 and 10. Half of them work, half of them don't in some meaningful way. So in that case, R would be 1. But, I think Ioannidis' point is that probably in a lot of literatures, R is a lot less than 1. If we're really in a world where R is greater than 1, like we're really, really confident that like 70, 80, 90, 95% of the hypotheses in an area are true, and we're really confident of it, and that's true, they really are going to have an impact, then there isn't as much learning to be done, right? Like we're in a field where we kind of already know most stuff. Like most of the hypotheses are already well understood. So he's really thinking of a world where R is less than or equal to 1 throughout this exercise. Like it's 50-50. Like we have a hypothesis, and there's sort of even odds whether or not it's true. So that's kind of a reasonable starting point. So he's going to start at like R equals 1 and sort of go down. And his claim, and again I think he's influenced by the medical field, is there's lots of research areas where R is much less than 1. So in the medical research field recently, where there's been massive mining of genomic data and just tons of really, you could say, undisciplined exploratory analysis about what the correlations are between certain genes and certain diseases, where there are like thousands and thousands of possible gene sites and hundreds of diseases, people are just running tons of tests. And Ioannidis would say that R in that sort of literature would be really small, like 1 over 100 or something like that. Like needle in a haystack research. So again, there's a range here where some well-defined literatures with well-defined theory where you have some sense of the setting, maybe R is close to 1, and in others maybe R is 0.1 or something, or 0.05. So that's kind of the range you should be thinking of, probably for most social science research. And then, if you just do the algebra, like in terms of converting these little R1, R1 and R0 into R, the sort of fraction of true relationships overall is big R over R plus 1. So that's going to be a really key term for us. That's like the plausibility of the hypothesis, basically, based on what we know. The other thing that's going to be very important in thinking about how to interpret a research result is the probabilities of different types of errors. So there are type 1 errors that we care about. false positives. I think everybody's very familiar with type 1 errors. They're the basis of our significance tests, and usually we're willing to tolerate a certain amount of false positives. Typically 5%. So this is the p equals 0.05 that everybody's familiar with. That's alpha here. There's also the probability of a type 2 error. So not a false positive, but you could think of it as a false negative. Like there is a relationship, but you don't find it. So there is a significant effect here, but maybe your sample size is too small, maybe there's a problem with the design, whatever, and you don't detect, the test suggests there's no effect, but there really is an effect. So 1 minus this false negative rate, 1 minus beta, is our statistical power term. In other words, how likely are we to find an effect if there really is an effect based on our research design? And in general, large sample sizes will help with statistical power, just because there's less sampling variation that comes into play. Basically, if you have a small sample, there's lots of sampling variation, and you can't say very much. If you have a sample of 4, God knows what the data is telling you. If you have a sample of 4,000, then maybe some of the noise evens out. The conventional wisdom for those of you who have or will design field experiments or lab experiments, the ideal, if you're putting together a proposal for the U.S. National Institutes of Health, they want to see power calculations where you claim you are powered to 80%. They want to basically see what sort of effect size you could legitimately estimate, or you'd expect to be able to detect with 80% power. That's like the rule of thumb power. Now, in reality, when people have checked the amount of power in actual designs, often empirical studies have much less than 80% power, even funded experiments. Probably a pretty decent study has 50 or 60% power. There's plenty of studies, small social psychology or experimental economics lab studies that are like really small sample, way underpowered, where maybe they have 20 or 30% power. Okay, so probably the reasonable range in most social science research, I don't know, making it up a little bit, is like 20 to 80% power. 20 is way too low. Maybe 50 or 60 is pretty typical for experiments, and 80 would be like you're pretty well powered. If you're more than 80% power, that's a well-powered design. So you're familiar with this. And then just for the thought experiment here in the Ioannidis paper, imagine there have been C findings in a literature. There are like C studies in this research area. He's not combining in any serious way across the C studies. He's not like thinking about the meta-analysis here. It's like, if I see a result that's out there, what should I take from that result? And he's going to abstract away from a lot of additional problems like file drawer problems and